Okay, so today we're going to continue our study on series. Okay, so let's just recap what we did so far. So the definition of what it means for a series to converge. So we say if an is a sequence. Okay, so the idea of a series we saw is closely linked to the idea of a sequence. So if these an is a sequence of real numbers, we define the partial sums. Okay, so the first thing we had to do was talk about this thing called the partial sums. By, okay, I remember what the partial sum was. It was given by, so the nth partial sum, okay, let's write it out. So an, let me just write out what this is. This is, of course, a1, a2, a3, a4, and so on. Yes, an, and we keep going. So the partial sums are defined by the first partial sum is just the sum of the first one term. The second partial sum is the sum of the first two terms. The third partial sum is the sum of the first three terms. Okay, so you get the idea. The nth partial sum is the sum of the first n terms. Okay, but after a while it becomes a bit tiring to keep writing all of this. So instead, we just write that the nth partial sum is the summation of ak. So k is a dummy index, meaning I could use whatever letter I want, where k goes from 1 to n. Okay, so it's just the sum of the first n terms. Okay, so these are what the partial sums are defined by. So we saw from a sequence of real numbers, we can construct a new sequence. This is called the sequence of partial sums. Okay. So now we say if the, or maybe I should say if this sequence if this sequence of partial sums, right? So now the sequence I'm talking about is Sn. So we went from An to a new sequence Sn converges to S, okay, where S is something is some real number. Okay, it could be any real number. Then we say the series or the infinite series. Okay, so sometimes you can leave out the word infinite. It's usually understood that the series is infinite, meaning you are adding infinite terms. Then we say that the series summation. So over here we could write an or we could write ak. Again, this letter doesn't matter because it's a dummy index. Then we say that the series converges okay, and write that the summation k goes from 1 to infinity of ak equals s. Okay, so anytime, I'm sure you all have seen series before. Anytime you see something like this, where you have a series equal to some finite number, this number here, what it really means, because of course we cannot sit and add infinite terms, what this number really means is that from these terms, ak, you construct the sequence of partial sums, okay? And this s that you see is just the limit of that sequence of partial sums. So that is what is meant by a series converges. Of course, this does not always happen. So otherwise, if the sequence of partial sum does not converge to S, so does not converge, we say the series diverges. Okay, so if the sequence of partial sum does not converge, then we say that the series diverges. In particular, if this sequence of partial sums is blowing up to plus or minus infinity, of course, this means that it diverges. It's just divergent to plus infinity or minus infinity. Then we write the summation of AK as k goes from 1 to infinity. You could put it equal to either plus or minus infinity, depending on what's happening to the sequence of partial sums. Okay, and the reason why this is a special case of the series divergence is because I could give you all an example. So just because the series, if I say I have a series that diverges, that does not always mean that it is divergent to plus or minus infinity. Okay, and the example, right? So an example is if I have this series, so the summation of minus 1 to the n, where n goes from 1 to infinity. Okay, so this is equal to minus 1 plus 1, minus 1 plus 1, minus 1 plus 1, right? And so on. So from this, you could see that the sequence of partial sum S1 is minus 1, S2 is 0, okay, S3 is minus 1, S4 is 0, and so on. So in this case, the sequence of partial sum diverges, okay, because it's given by a sequence minus 1, 0, minus 1, 0, minus 1, 0. That sequence diverges, but it's not divergent to plus or minus infinity. Okay, it's not divergent to plus or minus infinity. So what I'm trying to say here is that if someone tells you that a series diverges, you cannot just assume it's divergent to plus or minus infinity. Because what could happen is that the sequence of partial sums might just be oscillating between two numbers. Okay, so in that case, the series diverges. Okay, so the series diverges, but not to plus or minus infinity. Okay, and we saw a very important series last time, and that was a P series. Okay, so just recall again, because it's very important. What is a P series? A P series is a series of the form summation n goes from 1 to infinity of 1 over n to the power of p. Okay, and in this case, this value p could be any real number. So not just a whole number or a negative whole number, right? It could be any real number. And this series converges if and only if the value of p, so you need to put it in this form first, the value of p is strictly bigger than 1, then it will converge, and it diverges otherwise, right? So it diverges if and only if the value of p is less than or equal to 1, okay? And the best example of this again, is the divergent harmonic series, right? So this is the value when P is equal to 1. This is the divergent harmonic series. Okay. However, if it was 1 over n squared, then that series will converge. Okay. And what else did we see? We also saw that a very important result, which was if I have some series converges. Okay, so if I tell you I have a convergent series, then the terms that I am adding, these an, the terms that you are adding together, should be going to 0. So the limit of these terms as n goes to infinity should be going to 0. Okay, and the contrapositive here, remember the contrapositive is just another equivalent way of saying the same thing. So the contrapositive of this result is very useful. The contrapositive just says that if the limit of the terms are not going to 0 as n goes to infinity, then when you try to add them in an infinite series, it will diverge. Okay. So the contrapositive is always true. And I could put here note, it's important. The converse means the backward implication is false, right? The converse is false. That is, if the limit as n goes to infinity of the terms are going to 0, you cannot conclude anything about the series. Okay, if the terms that you are adding together in a series, if these terms are going to 0 as n goes to infinity, that does not immediately mean the series will converge. So if the terms go to 0, then we cannot say this series converges, right? Right? We cannot say the series converges. The counterexample or the best example to see this is the divergent harmonic series, right? Is the divergent harmonic series. Because this series diverges, it diverges to plus infinity, but notice that the terms that you are adding together as n goes to infinity are going to 0. Okay, so this is a counterexample for it. Right? So then we went on to look at, so now we're looking at different types of tests for whether or not a series converges. Okay, so there are many, many tests. Okay, there are many tests, each with their own condition. We just need the two very popular ones. That's the one we're going to focus on. One of these tests is called the comparison test. Okay, and if you pick up any book on advanced calculus or any book on undergraduate analysis, and you flip to the chapter on series, you're going to see so many different tests there, right? But there are some main ones. The comparison test says that if I have two series, an where n goes from 1 to infinity, and the summation of Bn as n goes from 1 to infinity. So if I have two series such that so the A's and the B's, they must be non-negative. So such that 0 non-negative means bigger than or equal to 0. So let's say the ANs are less than or equal to the BNs. Okay? Or, of course, you could write this as strictly less than. Okay? So you can write it with the equal sign, less than or equal, or strictly less than, it still works. Okay, so if you have two series where the A terms are being dominated by the B terms, and the A's and the B's are non-negative, right? So two conditions. If the BNs, right, so the bigger terms, converges, if the sum of those terms converges, then what can I conclude about the smaller term, the ANs? Then the ANs should converge, right? Because the ANs were smaller than the BNs. Then this series also converges. Okay. And the second one is you could think of it like the reverse situation. If the ANs now, the smaller terms, diverges, or let's say is equal to either, well, it will be plus infinity because the terms can't be negative. So if the ANs, the summation of them is infinity, then the BNs were the bigger terms. So the BNs should also be that. Okay, so the BNs is also infinity. Okay, so we use this when you are given one of these series, either the A's or the B's. You're going to compare it to another one and apply one of these results. And it will tell you whether or not the series you have is convergent or whether or not the series you have is divergent. Okay, so that's where we stopped up to. Okay, so before we move on to another test, that's ratio test, notice that this comparison test has within it a big sort of limitation. That is the terms, the A's and the B's in the series that you are using, cannot be negative, right? They need to be bigger than or equal to 0. So this is a big restriction because it's not always guaranteed that the series we have, the terms are bigger than or equal to 0. So if you have a series where the terms, some of the terms, maybe all of the terms are negative, or infinitely many terms might be negative, is there a way to apply the comparison test? Okay, and that gives rise to, so what we're going to start talking about today, the first thing is something called absolute convergence. So definition, let AN, so AN is just your regular series, be a series or infinite series of real numbers. We can construct, so from this, we're going to construct a new series. So I could just say, if this series, where instead of adding up the ANs, I'm adding up the absolute value of the ANs. If this series converges, then the original series is said to converge absolutely. Absolutely, because we use the modulus or the absolute function in it. Converge absolutely, or be absolutely convergent. Okay, so let me just show you what is this new series that I wrote down, right? What is this new series that I wrote down here? So the original series, okay, the original series is given by the summation of ANs. Now these ANs could be positive, negative, zero, it doesn't matter, right? These ANs could be any real number. So this is A1 plus A2 plus A3. Again, we keep going plus AN and we keep going, right? So from this, we form a new series. Okay, so instead of looking at that old series, we are going to look at this new series, where instead of adding up the A's, I'm adding up now their absolute value. So modulus of A1 plus modulus of A2 plus modulus of A3. Okay, right? So what is so useful about this new series where I'm summing up the absolute value? Well, notice that all of the terms in this new series, all of the terms that you are adding up are non-negative, right? Because all of these terms are the modulus of some number. Remember, the modulus is always bigger than or equal to zero. So what's so special about this new series? What's so good about it? All of the terms in this new series, regardless of the original series, so it didn't matter what the ANs were in the original series, all of these terms in this new series are all bigger than or equal to zero. Okay, so I'll put that here. Note all the terms in this new series are bigger than or equal to zero. Okay, so from this, if the original series had negative terms, we were not allowed to use the comparison test. The comparison test only works if my series only has non-negative terms. So if some of the terms happen to be negative numbers, what you could do is form this new series where all of the terms in this new series are bigger than or equal to zero, then apply the comparison test to this new series, which means that there must be some link between the original series and this new series with the absolute terms. So what is the link between these two series? Okay, otherwise, if there was no link between it, then this new series with the absolute value would be kind of useless, right? There must be some link between it. So the link between it is given by this result. Okay, and it says that if this series with the absolute terms converges, then the original series converges. Okay, so if okay, so if the series with the absolute value converges, then the original series will converge. Okay, I'll put it here one time. So note, like many things we saw before, the converse is not true. The converse is not true. That is, if the original series converges, then this new series where I am summing the absolute values may not converge. Okay, so if the original series converges, we cannot say anything about this new series with the absolute value. However, if the series with the absolute value converges, then the original series is guaranteed to converge. Okay, and the proof, we will go through the proof because it's not too difficult. Proof, we're going to use Cauchy's convergence criterion for series. Okay, we discussed this last time. So we're going to say, suppose actually we don't even need this. Okay, so suppose this series, okay, converges, okay. Then by Cauchy's convergence criterion for series, for any epsilon bigger than 0, there exists a natural number n such that for two other natural numbers, so maybe I should have used k here because I want to use n as the next index, right? So let me just use k. Of course, these are dummy variables, so I could switch them out for any other letter, such that for n and m, so I want to use n over here, being two natural numbers where n is the bigger one, we have that the terms, the modulus of these terms, a m plus 1 plus a m plus 2 plus all the way up to a n is less than epsilon. Okay, so this result here is referred to as Cauchy's convergence criterion for a series. It tells me what happens if this series converges. Oops, sorry. So you see, this series, it's the terms are the absolute values of an, right? So these terms that I am adding up should be the modulus, right? These are the new terms. And it's saying that the modulus of this is less than epsilon, right? Right? Why am I taking the modulus of these terms? Because what series converges? What do these terms look like? They look like the modulus of AK. Let me make this better. So it's the modulus of these things, right? Of course, I don't need to put the outermost modulus because I'm adding together non-negative numbers. So the modulus of a non-negative number is still that number, right? Right, so this implies, so what happens now if I look at just the modulus of the original terms? Okay, so these terms plus a m plus 2 plus the original terms without the modulus, right? So I'm not taking the modulus of these individual terms, I'm just looking at them as if. What happens if I add them together and I take the modulus of that? Well, if I apply triangle inequality, this is less than or equal to the modulus of am plus 1 plus the modulus of am plus 2 plus all the way up to modulus of an, right? This is by triangle inequality. Okay, by triangle inequality. And these terms are all bigger than or equal to 0, right? These terms are all bigger than or equal to 0. So if I add them together, the result of the sum is bigger than or equal to 0. which means that it is equal to its modulus. Okay, it's equal to its modulus. So I could put the modulus sign around it, right? And this thing over here is just this guy, right? So that is just less than epsilon, right? And that right there is, so then we say by Cauchy's convergence criterion for series, the original series converges. Converges. Okay, which is what I wanted to prove. Right, so if the series of the absolute value converges, then the original series converges, but the converse is not true. Okay. Now we'll see some examples of the converse not being true later on. All right, so let's go into the slide. Okay, so what I said was the comparison test only works with series of non-negative terms. Okay, and we saw if a series has some negative terms, it's often convenient to then consider this new series where I add together the absolute value of those terms. Now, and I wrote down before, if this new series converges, then the original series is said to converge absolutely or be absolutely convergent. However, if the original series converges, we are not guaranteed that the series with the absolute value will converge or diverge. But if the original series converges and the series with the absolute value diverges, then the original series is said to be conditionally convergent. Okay. And over here is what I just proved. If a series converges absolutely, then it converges. Right, so this is what I just proved over there. Okay, and here's an example of that. So you're given this series. All right, remember, anytime you see a series and it has a term in it, -1 to some power n, or maybe it's n plus 1, don't get scared. All this -1 to that power is doing is every other term, it flips the sign. So one term will be positive, then the next guy will be negative, then the next guy will be positive, then the next one will be negative. So that's all this -1 to some power does, to some integer power does. Okay, I cannot apply comparison test here because every other term will be negative, right? And remember, comparison test only works with non-negative numbers. However, I could take the absolute value of this series. Okay, so let me consider this a new series where I take the absolute value of the old series. Okay, the absolute value distributes over the numerator and denominator, right? The absolute value of -1 to the n is just 1, so that goes away. N is always positive, so the modulus of n is just n. The square root that you see down here is the positive square root. So the modulus of that is just the positive square root, right? So the modulus, essentially what the modulus does when you take it on both sides, well, when you take the modulus of this term, is that the modulus kills this -1 to the n term. It gets rid of it for you. Okay, so this series here, I can apply comparison test to it. Right, I know n to the power 7 plus 2 is bigger than n to the 7. So I could square root both sides and flip them. And if I do that, then I get n over square root n to the 7 plus 2 is less than n to the -5 over 2. Okay, and this is a p-series, so you need to write it as a p-series. This is 1 over n to the power of 512. 512 is bigger than 1, so this p-series will converge, right? So since this guy is a convergent p-series, remember the form of a p-series. I know you're seeing the power over here, and you're thinking, wait, isn't p in this case minus 5 over 2? Right? Uh, right? Where is it? P-series, right? So for p bigger than 1, it converges. For p less than or equal to 1, it diverges. So you're seeing minus 5 over 2. But remember, for a p-series, it has to be in this form. So when you see the summation of n to the power of minus 5 over 2, you need to write it as the summation of 1 over n to the power of 5 over 2. So p is 5 over 2, which is bigger than 1. Therefore, it converges. Okay, so the value of PD is not minus 5 over 2. It's positive 5 over 2. Right? So what's happening? When the series of the absolute value by the comparison test turns out to converge. And we just proved a result that said if the series of the absolute value converges, then the original series, which is what I'm interested in, will also converge. Okay, so by the comparison test, the series of the absolute values is convergent, which implies that the original series is absolutely convergent, and absolutely convergent means you are also convergent. Okay, so it's a very handy tool if some of your terms, or maybe infinitely many of your terms that you're adding together happen to be negative. What you could try is just take the absolute value of it, right, and see if it converges absolutely. Okay, so here's the next useful test, the ratio test. And this one is saying if you have some series, an, so this is a series of non-negative terms, oh sorry, non-zero terms. So for the ratio test, some the terms are allowed to be either positive or negative, right? They just cannot be zero. Okay, so the ratio test, you don't really have much restrictions about the terms. What you do is you calculate this number L. So L is just the limit of the n plus 1 term over the n term. You take the modulus of that, simplify that expression, and then take the limit, right? So I know you all from your first year calculus courses, you're good at taking limits. Okay, so you just take the limit of that, and that gives you a number L. Now, depending on what this L turns out to be, it will tell you whether or not this original series is converging or not. Okay, so if that L is less than 1, strictly less than 1, then the series converges absolutely. And of course, you know, convergent absolutely means you also converge. If this L happens to be strictly bigger than 1, then the series diverges. And if this L happens to be equal to 1, then the test doesn't tell us anything, right? It doesn't give us any information. So if it is equal to 1, that means you need to try something else, try another test, okay? So this is the second test that you need to remember, ratio test. So you need to know the comparison test and you need to know the ratio test. Okay, or at least the how to apply it, not the proof of it, but you need to know how to apply it. Right, so from the ratio test, there's another similar test to something called the entry test. So we'll go through it. These are just examples of more elaborate sort of tests that you will come across. We'll go through it, but you wouldn't need this one. The N-root test, again, you have some series. We want to know whether or not this series is converging or diverging. So what you could do is, like the ratio test where we have to determine a number called L, in this one we need to find a number called alpha. Now alpha is just the limit of the absolute value of these terms to the power of 1 over n. Okay, so in general, depending upon what the terms here are, the ANs, this limit may not be so easy to compute, because if you look at it, whatever term you get for AN, after you take the modulus of it, you need to raise it to the power of 1 over n and take the limit as n goes to infinity, right? So that might be a difficult limit to evaluate. However, if alpha is strictly less than 1, so the conditions for alpha are exactly the same as the conditions for L. So if L was less than 1, the series converges. If alpha is less than 1, the series converges. If L was bigger than 1, then the series diverges. If alpha is bigger than 1, the series diverges. And remember, when L was equal to 1, it didn't tell us anything. So if alpha is equal to 1, this test gives no information about its convergence or divergence. So the results are similar, except you're calculating a different limit. Okay. So the proof is as an exercise for you to try. Okay, so I put here, if you're stuck trying to prove this one, you could just look up the proof in any textbook or on the internet. Okay, it's a very interesting proof. So the reason why the conditions on alpha are so closely tied to the conditions on L, why they look the same, is because one of them is used to prove the other. Right? I can't remember which one is used to prove which. So I put here as a remark, whenever the ratio test determines convergence or divergence, so does the N-root test. And the ratio test is often easier to apply than the N-root test, right? It's easier to work out that limit. However, the N-root test works for a more general class of series. What do I mean by that? Well, let's go back to the N-root test. In the N-root test, what are the conditions for the AN that I am allowed to apply this test? Well, it didn't give me any condition, right? This just says, given a series, summation of AN. So the terms AN could be, some could be positive, some could be negative, some could be 0. It doesn't matter, right? We could work out what this alpha is. So in the ratio test, the ANs need to be non-zero. Okay, so the ratio test, it has to be non-zero. The N-root test, no restriction. Okay, so that's what I mean by this second point here. So here are some examples of the N-root test. Oh, sorry, this is the ratio test. Right, so we're given a series, summation of AN, where the ANs are -1 to the N. Okay, of course, I told you all what this -1 to the N does. It basically flips the sign. So one term is positive, then the next guy is negative, then the next guy is positive, next guy is negative. Okay, divided by 2 to the n factorial. So I want to figure out, does this series converge or diverge? So let's try to use a ratio test. Now the ratio test, I need to figure out what is the limit of the modulus of AN plus 1 over AN, right? So first, work out what is the modulus of AN plus 1 over AN. So the n plus 1, you look at AN, and anywhere you see n, you substitute n plus 1, right? So this first part here is the n plus 1 term. Then you divide by AN, right? And they already told us what AN is. So you know if you divide by an, if you divide by something, that's the same thing as you multiply by the reciprocal of it. Okay, so if we divide by an, that's the same thing as multiplying by, and we flip an, right? So you flip an. Okay, so the -1 to the n plus 1 and -1 to the n, some stuff cancels. 2 to the n cancels with 2 to the n plus 1. Okay, so you apply your rules of indices and you will get some simplification. N factorial over n plus 1 factorial gives n plus 1. Okay, maybe I should show this. Okay, so let me show how to do this one. Okay, so we are given the summation as n goes from 1 to infinity. What was it? -1 to the n all over 2 to the n factorial. Okay, this is my an. So an plus 1 is equal to -1 to the n plus 1 all over 2 to the n plus 1, n plus 1 factorial. Okay, so this implies what is the modulus of an plus 1 over an. Okay, so that's the modulus. The an plus 1 term to -1, 1, 2 to the n plus 1, n plus 1 factorial. And the nth term, the an term, sorry. So we divide by an, which is same thing as multiplying, and we flip an. So it's 2 to the n factorial all over -1 to the n. Okay. So this term here is an plus 1, and this term here is 1 over an. And when you multiply them together, you of course get an over an plus 1 over an. Okay, so we can write out the intermediate steps. Right, so let me just move some stuff around. So I get -1 to the n plus 1. I'm going to put the -1 to the n right below it. I get 2 to the n, and let me put 2 to the n plus 1 right below it. So I'm just moving them around so you'll see how things cancel. I get n factorial over n plus 1 all factorial. Okay, and of course you know your rule of indices. So n plus 1 minus n is 1. You get -1 to the 1. N minus, you get n minus n plus 1. So I'm looking at the coefficients of 2. Right? And when you divide, you subtract the index, right? That's the rule of indices. You all know a to the n all over a to the m is equal to a to the n minus n. So this will give -1. So I get divided by 2, right? And n factorial, right? N factorial is equal to 1 by 2 by 3 by all the way up to n. N plus 1 factorial is 1 by 2 by 3 by all the way up to n by n plus 1. Okay, so if you divide these two, right, if you divide these two, 1 will cancel with 1, 2 will cancel with 2, 3 will cancel with 3, n will cancel with n, and you will only be left with n plus 1 in the denominator. Okay, so over n plus 1 modulus. So this is the modulus of -1 divided by the modulus of 2 into n plus 1. Of course, the modulus of -1 is +1. And 2 into n plus 1 is always positive. So I could remove the modulus. Okay, so we get this term. Okay, therefore, L, which is the limit of this term that I just worked out as n goes to infinity is the limit as n goes to infinity, and this is what I just worked out. 1 over 2 into n plus 1. So as n goes to infinity, the denominator is going to infinity. So 1 over something that's going to infinity is going to 0. Okay, so this is equal to 0, which is strictly less than 1. Okay. Right, so L is 0, which is strictly less than 1. And when L is strictly less than 1, the ratio test tells me that the series converges absolutely, hence it converges. Okay, so that's the application of the ratio test. Okay, so let's just run to the next application of it. So another series, we are given the summation of an, where the terms now look like minus 3 to the n over n squared. So again, we need to figure out what is the modulus of an plus 1 over an. So this first term is the n plus 1 term. Divide by an is the same thing as multiply by 1 over an. So you flip an and multiply by it. Apply your rule of indices. So minus 3 to the n cancels with minus 3 to the n here to get minus 3. Now don't go and write, because you're second year at least university students now. So don't go canceling out squares from this, right? I don't want to see. What I'm saying is I don't want to see anything like this. Right? Square. Right? I don't want to see anything like that. Right? That's nonsense. So don't go doing that. Can't cancel powers like that. Okay. So in the numerator, I will get minus 3 to the n squared. In the denominator, where you have n plus 1 all squared, expand it out, right? So a squared plus b squared plus 2ab. So expand it out. And, well, the modulus gets rid of the minus sign there. And what they're doing is, well, if you have to take the limit of something that looks like this, as n goes to infinity, what's the trick to do? You need to find the highest power of n. In this case, the highest power of n is n squared. And you divide every term by n squared. Right? So divide every single term by n squared. And then when you take the limit as n goes to infinity, 2 over n is going to 0. 1 over n squared is going to 0. So all that you are left with is 3 on top and 1 below. So 3 divided by 1 is 3. So L is equal to 3. And since L is strictly bigger than 1, the ratio test tells me that this series is going to diverge. Okay, so by the ratio test, this series diverges. Now, if you have a series that looks like this, n to the n, 2 to the n squared. So usually if you have to use one of these special tests, like the nth root test, this helps if your terms have a particular form to them. So in this case, if you use the ratio test over here, maybe you might get it to work, I don't know. But this term is a lot easier to use the nth root test. Okay, so for this series, we could use the nth root test. So usually if you have to use this one of the the first set of tests you should always try is either the comparison or the ratio. But if you have to use another one, maybe the question might give you a hint. As in hint, try nth root test or something like that. Okay, so I'll leave this example for you to go through. Okay, like I said, the nth root test, you don't really need to know that, right? But this one is an application of the nth root test. All right, so there's also another useful test. This one is called the alternating series test. And it's basically this minus 1 to the power of n coming back in a series. Okay, so it's saying if an is a decreasing sequence, so decreasing sequence means the terms are getting smaller and smaller of positive numbers and they are going to zero. Okay, then the series where I am adding together minus 1 to the n of an converges. Okay, so let me see if I could draw this one for you. All right, so this is a useful result. Okay, so you have a couple conditions. The first condition is um, an is a decreasing sequence of positive numbers. The limit of these numbers are going to 0. Then the summation of not an, it's minus 1 to the n an converges. Okay, so what does this look like? Well, sub in when n is 1, you get minus an, minus a1. When n is 1, you get minus a1. When n is 2, you get plus a2 minus a3 plus a4 minus a5 plus a6. Right, so that's what I meant by when I said this minus 1 to the n. What it's doing is every term, it's changing the sign. Okay, so it's changing the sign as you go along. Right, converges. Okay, so the alternating series test gives us a way to figure out whether these alternating series converges. And just like we have the divergent harmonic series, we also have the alternating harmonic series. Okay, so this is an important series. And this one's called the alternating. So we know what the harmonic series is. That's just the summation of 1 over n. The alternating harmonic series is where the signs alternate. So it's the alternating harmonic series. Right? And it's just the summation. N goes from 1 to infinity. So instead of it being 1 over n, that will be the divergent harmonic series. What you do is minus 1 to the n. Okay, so all this is, it's minus 1 plus a half minus a third plus a quarter minus a fifth plus a sixth and so on. So it's the original harmonic series, but now you flip the sign of every other term, right? And this actually converges. So the harmonic series diverges, but the alternating harmonic series converges, right? How do you show the alternating harmonic series converges? You apply the alternating series test, okay? Because an, in this case, an is 1 over n. An is a decreasing sequence of positive numbers. The limit of 1 over n is going to 0, right? So therefore, this series converges. Converges, apply the alternating series test. However, I'll put here note, this series, the alternating harmonic series, is conditionally convergent. Conditionally convergent means the series is going to converge, but when you take the absolute value of it, of the terms, that series diverges. So is conditionally convergent since what happens if I take the summation of the absolute values of these terms, right? What is this equal to? Now remember what the absolute value does to this minus 1 to the n. The absolute value gets rid of the minus 1 to the n. So you just get 1 over n. And of course, we know this is the divergent harmonic series, right? So the reason why the alternating harmonic series is conditionally convergent is because the series, the original series, converges. But when you take the summation of the absolute value of these terms, you end up with a divergent series. What's a divergent series? It's the divergent harmonic series. Okay, so remember this one, because if I ask, give an example of a series that is conditionally convergent, you will give me this one. It's the easiest one. Okay. All right, so we also have that's another sort of fancy limit, not limit, series test. Okay, so this one is called the limit comparison test, right? So I will leave you all to go through this one, right? We don't need this one, right? But you could also read it through if it's useful in some circumstances, right? Okay, so the last topic, right, in a course is what is known as power series. Now, everything that we did so far in this chapter series essentially leads up to this thing called a power series, right? So everything we did so far is needed to understand this series. So a power series is a special type of series, okay? So let's just look at it first, and then I'll sort of explain the idea behind it. So let an be a sequence of real numbers and x0 be some fixed real number. So x0 is a fixed number. A series of this form, summation n goes from 0 to infinity of an into x minus x0 to the power of n, is called a power series. So how does this differ from what we were looking at before? Power series. Okay. So notice in all the series we were looking at before, it was just a list of numbers, right? So an was just a1 plus a2 plus a3. Oh, sorry, the summation, right? So all of these numbers you are adding were fixed. In a power series, there's a variable, right? There's a variable x that you could tune. So a power series, right? So a power series is a series of the form right. So let's just look at the terms of this series. So it's a summation. So the first thing to notice is n starts at 0. Now, so many students, when they are doing this for the first time, they encounter power series where n starts at 1 and they don't know what to do, right? where x is, okay, I can't write it here. Right, so what do we want to note? So let's note a couple of things about this guy. So the first thing to note that I want you all to remember is that the index n here does not have to start at 0, right? So the index for the dummy variable n does not need to start at 0. Okay, and the reason for that is because maybe, for example, there's a summation at n from 3 to infinity of something, right? That could still be a power series because there's always a way to basically reorder the index. So we're not going into that, right? But there's also a way to, there's always a way to reorder the index such that you could convert this into a new series where the dummy variable or the dummy index now begins at 0, right? You could always change the index. You could always bump up the index or lower the index accordingly. So the first thing to notice is if you come across a power series where the index n does not start at 0, don't panic. It's still a power series, right? It just doesn't start at 0. That's okay. These ANs are real numbers. So maybe I should say fixed real numbers. Fixed real numbers. Okay, of course, it's real numbers for us because we are only focusing on real numbers for this course. Of course, the index n changes. X0 is some fixed real number, and it's called the center. So remember neighborhoods? Remember neighborhoods? Let's go back to neighborhoods where you had an epsilon neighborhood around some point. So here is epsilon. So epsilon was called the radius, and x0 was called the center of the neighborhood. So we will see why that terminology is coming back. Sometimes referred to as the center, right? We'll see why in a bit. They use the word center there, right? It links the neighborhoods. X now, so the main difference between a power series and what we were summing before is that we now have a variable x. X is a variable. Okay, so depending on the value of x that you throw in, the series may converge or diverge. So what I want to say is the series we get depends on the x value. Okay, so if you take x equal to 1 and you plug it into a power series, you get one series. If you take x equal to 7, you plug it into a power series, you get a next series. Okay, so a power series is sort of like we were generalizing what we had before. Now the power series depends on the value of x, right? Okay, so the numbers an are called the n coefficient of the series. Okay, for example, the geometric series, which is just x to the n. Okay, so it's usually written as r, but r and x, same thing. Okay, this is a power series where the ANs are all set to be equal to 1. Okay, and what is x0? Okay, so yeah. x to the n, where n goes from 0 to infinity. Right, so what you first need to do is write this in the form of a general power series. So it's an, which is 1 by x minus 0 to the n. Okay, so this is your an terms. This is your x0 term. Right, so you need to first write it in the form of a general power series to identify what is an and x0. Of course, you don't always have to do that. With time and practice, you may just look at the power series and know what the ANs are, you will know what the centers are. But when you're starting out, it helps to first, whatever series they give you, first write it in this general form and identify what is AN, identify what is x0. Okay, now remember that for a geometric series, it only converges if the value of x, right, or the ratio that you are multiplying to get to the next term, if this value is between -1 and +1, and it diverges otherwise, this is giving us a hint as to how this general power series behaves. You see, this general power series, the ANs are fixed from the beginning. Here, the ANs we will know x0 is fixed, but depending on the value of x that we throw into this series, so notice for each value of x you put in, you get a new series of real numbers. Okay, that new series of real numbers for a particular value of x may or may not converge. Okay, so we are interested in for what values of x does the power series converge? Okay. So the main question is for what values of x does, or maybe I should put will, a given power series converge? Okay, and you all have already come across power series before. Your Maclaurin series, right, which is a general form of a Taylor series. So this, if you all ever see this Taylor series, that is a next example of a power series. Right, so example, this is your geometric series. Taylor series. Let me write that out. So there's not Taylor Swift, okay? That's Taylor series. Taylor series. Okay, so all of these are general examples of power series. Okay, a Taylor series is just a power series where the ANs are equal to the derivative, right? I think it's the nth derivative of x all over n factorial. Okay. Yeah, so you don't need to know that for now. Right, so a Taylor series is a general form of a power series where the coefficients are dependent upon the function and its derivatives at a particular point. So we are concerned with for what values of x will a given power series converge or diverge? It turns out that there is a theorem that tells us exactly what values it will converge. And when a power series converge, it converges very nicely, right? It's given by this. It converges in a radius, something called the radius of convergence. So when dealing with a power series, the first thing that you should do is find out what is this number, the radius of convergence, R. Okay, so the radius of convergence, R, for a given power series, so notice we don't do anything with the x's. All we are focused on are the a's, right? So we just want the a and 2. So R is equal to the limit as n goes to infinity of the modulus of an over an plus 1, provided that this limit exists. Now, try not to mix this up with the L from the ratio test, right? Let me go all the way back to ratio test. Ratio test, right? You see this L? The L in the ratio test is the n plus 1, an plus 1 over an. For the radius of convergence, it's the same thing, but it's an on top and an plus 1 below, right? So this is for a ratio test. For the radius of convergence, you see, it's an on top, an plus 1 below, right? So please don't mix that up, otherwise you'll get 1 over the answer you should get. Okay, so this theorem, after you find this number, R, this radius of convergence, this term tells us how it converges. It says that a power series, right, not just converges, it converges absolutely if you take an x value within a distance r of this center x0 and diverges outside. I'll put here a power series, right? And again, it does not have to start at 0. The summation does not have to start at 0. Whenever for x value, whenever x values is within R and diverges for x values bigger than R, where, what is this R? It's the limit as n goes to infinity of an over an plus 1. Okay. So let me show you what that looks like. Actually, this thing is linked a lot with complex analysis, right? Because in that one, you also have power series, but it's complex in the complex plane. So what's happening is, let's say here is your x0, right? Let's say you worked out this value r, and let's just say it's finite, right? We'll see in a bit, it does not have to be finite, but let's say it's finite. So let's say it's r, right? R here and R here. So over here and over here. So it's a neighborhood, right? Remember neighborhoods? X0 plus R and X0 minus R, right? It's neighborhoods. We go back to this neighborhood stuff. So it's saying for any X value inside this neighborhood, it will converge. Inside the neighborhood, centered X0, radius R. And it diverges outside. Right, I should say it not only converges, but converges absolutely, right? Because absolute convergence means convergence, but it's like a more stronger form of convergence. Okay, so once you find this value R, then you could immediately tell me an interval where it converges. This is called the interval of convergence. Okay, so the neighborhood, okay, which is center x0 radius r, which of course you know is x0 minus r, x0 plus r, is called the interval of convergence. Of the power series. Okay, or the interval of convergence of a power series. Right, so once you take any x value inside this interval and you throw that x value into your power series, it will converge. If you take an x value outside of this interval and you throw that x value into your power series, it will diverge. What about x values at the boundary? Right? Notice this theorem does not tell us what is happening at x equal x0 minus r and at x equal x0 plus r. It doesn't tell us what's happening. Right? So I'll put here note a power series may or may not converge at the boundary of this interval. That is at x equals x0 minus r and x0 plus r. Right? At these two x values, some power series will converge, some of them may diverge. We don't know. Okay. Right, so a power series converges absolutely whenever x is in a neighborhood centered x0, radius r. Right, and this follows from the ratio test. Now, this r, right, this limit, when you're working it out, it could be infinite, right? In fact, if this value r turns out to be equal to infinity, that is the best case scenario. When r is equal to infinity, when this limit equals to infinity, it means that the power series will converge for every single x value you throw in. It doesn't matter the x value. Any x value you throw in, it's going to converge. So r equal infinity is the best case scenario. What's the worst case scenario? So notice if you throw in for x, if you set x equal x0, this term will become x0 minus x0, which is 0, right? So you'll get an multiplied by 0. Anything multiplied by 0 is 0. So at x equal x0, you are just summing together zeros, which of course is convergent. It's a series that is equal to 0. So at x equal x0, the power series always converge. If I give you any power series, it is always going to converge at the center, right? Because it will always converge to 0. If this radius r, this limit, works out to be 0, right? That's the worst case scenario. That means it only converges at one point, the center. Right, so that's discussed over here. If r, which is a limit, works out to be infinity, that doesn't mean you're wrong. Maybe it is infinity. Then the power series converges absolutely for all values of x. If r equals 0, that's the worst case scenario. the power series converges, okay, absolutely, it doesn't matter because it's converging to 0, only at x equal the center. Now, the set C of values for which the power series converges is either the center alone, all of the real numbers, that's when r equal infinity, or a bounded interval centered at x0, that's the interval of convergence, right? So C is called the interval of convergence. And I think I wrote that here. Yeah, interval of convergence. Now at the value, at the boundary, when x minus x0 is equal to r, this theorem tells us nothing about the convergence or divergence of the series at the boundary points of the interval of convergence. So it is usually necessary to check these points individually for convergence and absolute convergence. So what that means is, when you're given a power series, after you figure out what r is, the radius of convergence, you will then write down the interval of convergence. But what about the endpoints of this interval? You need to check those endpoints individually. Okay. So here's, we'll do 2 examples, right? They're very similar, very easy, nice, easy examples. Okay, so we're given this power series. Now, how do you identify it's a power series? Well, it depends on x to some power, right? The moment you see a series with an x in it, a variable in it, to some power, well, some integer power, that is a power series. So what you need to do is first write this in the form of a general power series, right? So write it in this general form. And if you compare to this general form, we will see that the coefficients an are 1 over n factorial. And x0, there's no x0 over here, so x0 is 0. So the first thing you need to do is write the given power series in the general form and figure out what is an, what is x0. Once you figure out what an is, you then need to determine the radius of convergence. So that is by this limit. So it's limit modulus an over an minus 1. Okay, so you look at this limit and you will get it equal to infinity. Best case scenario, when the radius of convergence is equal to infinity, you don't have any endpoints to check, right? Because why don't you have any endpoints to check? What are the endpoints of the real numbers? There are no endpoints. Okay, so therefore, the interval of convergence is all of the real numbers. So this particular power series, x to the n over n factorial, which some of you might recognize, this is what? This is e to the x, right? This is the power series expansion of e to the x, right? So e to the power series of e to the x is entire. It exists for all values of x, right? So this series converges absolutely on R. Why does it converge absolutely? Because remember, this theorem tells us that a power series converges absolutely inside the interval of convergence, not at the boundary points, inside the interval. Okay, in this case, the interval is all of the real numbers. So it converges absolutely on all the real numbers, right? Best case scenario. Now, this was x to the n over n factorial. What if I remove the factorial? So same series, but where you see n factorial, remove the factorial. And now we get x to the n over n. What about this power series? So again, compared to the general power series, and again, n does not need to start at 0. In fact, in this one, x to the n over n factorial. Yeah, so that's a typo I have to fix. So this one, summation n goes from 0 to infinity, x to the n over n factorial, right? So let's write out a few terms. When n is 0, I get x to the power of 0 over 0 factorial plus x to the power of 1 over 1 factorial plus x to the power of 2 over 2 factorial. You get the point. X to the 0, anything to the power of 0 is 1. Right, so recall e to the power of 0 is 1, and 0 factorial by definition is 1. So this first term is actually 1, right? X to the power of 0 over 0 factorial is actually 1, plus x squared over 2, plus, and you keep going. The second example, right, example 1. So what is the typo that I made here? X to the n over n. So the first term is x0 over 0 plus x1 over 1 plus x squared over 2 plus, what is the mistake here? What is this term equal to? So it's not equal to anything. You can't put that. This is 1 over 0, right? So this term is undefined. So what I should have written, right? So this is a typo. What I should have written was the summation of x to the n over n, where n starts at 1. Right? You need to start n at 1, not n at 0, because you can't plug 0 into this. This is still a power series, right? Remember, the index that you start at doesn't matter. It's still a power series, right? So just note that in this one. So n should start at 1 over here, not 0. Okay, so we could compare it to a general power series, and we see that an is 1 over n, and x0 is 0. Okay, so the next step is to calculate r, the radius of convergence. So again, that's given by this limit, right? So you all know how to do these limits. So that limit is equal to 1. The radius of convergence is 1. So now write down the interval of convergence, right? So therefore, the series converges absolutely when, so you don't need to write it down like this, right? If you want to, you just give me it like in the form of an open interval. In this case, the radius of convergence is 1, and the center is 0, right? So here's x0, here's r equal 1, right? So here's 1, and here's minus 1, right? So therefore, the interval of convergence well, technically, this isn't the interval of convergence because I don't know about the endpoints. But I may not write it, right? So all I could say is this implies series converges absolutely, right? On minus 1, 1, open interval minus 1, 1. Okay. So now we have endpoints. The endpoints are, of course, x equal minus 1 and x equal to 1. What is happening at those endpoints? So now we need to check convergence at the boundary of this interval. So the boundary means the endpoints. So when x equal 1 and minus 1, take those values and plug it into the original power series. So when x is equal to 1, this is your series. Plug in x equal to 1 and see what happens. When x is equal to 1, what do I get? I get 1 to the power of n. Any 1 to any power is always 1, right? So that's just the series 1 over n. Again, it should start at 1, right? N equals 1, right? But we know what this series is. This is the divergent harmonic series. Therefore, it does not converge at 1. What about when x is equal to -1? When x is equal to -1, take -1 and plug it into x, right? And we get this series, which, so now we see why it's important to know the divergent harmonic series, the alternating harmonic series, and P series, because they come up a lot when you do this power series sort of thing, right? So this series is the alternating harmonic series, which is convergent. Therefore, the interval of convergence is, so it's the original interval, open interval -1, 1, but we need to add a point into it. You see, it converged at -1, so I need to add -1 to it, okay? So, and also at x equal to -1, right? So therefore, the interval of convergence is equal to -1, 1 union singleton -1, which of course is -1, 1, right? So we need to check the endpoints, right? Now this one is a little bit more involved, right? So now we have some things like what you may see on an exam, right? And notice n is starting at 2, right? But it's still a power series, right? If n starts at 2. Okay, so again, what do you need to do? Compare to the general form of a power series. So an is everything you see before the x plus 2 term, right? This entire mess is an. X0, so x0 is -2. Okay, because the general form of a power series is x minus x0. What we have is x plus 2. Okay, therefore x0 is -2. So once you find an, you then need to work out r, right? We need to work out this limit. So it's the an term divided by the an plus 1 term, right? So you flip it. And some stuff will cancel down, right? You don't get much cancellation, right? So I trust you all know how to do these limits. So this first term, you could divide through every term by n squared. This second term with the square root, the highest power inside the square root is n to the 6, right? So divide through every term inside the square root by n to the 6. Yeah, so all I did from here is this first term. Divide every term by n squared. This second term, so inside the square root, forget about the square root. We inside the square root. Divide every term by n to the power of 6. Right? Now take n to infinity. Anything, so 1 over n goes to 0, 2 over n goes to 0, 4 over n to the 6, that's going to 0 very fast, right? So all of these things go to 0. And when everything settles down, you will get 1/2. Okay, so r is equal to 1/2. The radius of convergence is 1/2. Right? So for example 3, the radius of convergence is 1/2, and x0 was -2. So what is the interval? It's not the interval of convergence, but where does the power series converge? So here's -2, and I go 1/2 this way, and 1/2 this way. Okay. So this is -2 plus 1/2. This is -2 minus 1/2. Right? So therefore, from this I get -2 minus 1/2 -2 plus 1/2. Okay. right? So hence the series converges absolutely when x values is within this range. So this modulus x minus x0 less than r, modulus x plus 2 less than 1/2. You don't need to write that. All you need to do is give me the open interval, right? So we know to get the open interval. It's just the neighborhood centered minus 2, radius 1/2, right? So we hold that out. And so this is minus 512 minus 302. Okay, so that's what we are after. So it for any x value you give me inside of this interval, it will converge absolutely. Now, what about the endpoints? Okay, so take x values at the endpoints. So take x equal to minus 5/2, plug it into your series, right? So it's a bit of a mess right now when you plug it in. Okay, but some stuff should simplify down, right? So some stuff will simplify and you get this series. N squared over square root n to the 6 minus 4. So now is where all those tests we did before, the comparison test, the ratio test, right? All of those tests now come into play. So this n squared over square root n to the 6 minus 4 is bigger than n squared over square root n to the 6, which is 1 over n. And 1 over n, if you sum 1 over n, that diverges. Therefore, if I sum this original series, it will also diverge, right? So by comparison test, this series diverges. Hence, the power series is divergent at x equal minus 5/2. Okay, so let's check the other point at x equal minus 3/2. So again, take your power series, plug in for x, minus 3/2. Some stuff will simplify down, so simplify it. Right, and we get this series here. This series, notice it has this minus 1 to the n. That's a little bit troublesome for us. So let's take modulus on both sides to get rid of it, right? So let's consider this new series. Okay, so the series of the absolute value. Notice that this series, when you take absolute value, this new series you get was the one we just worked out. What? Summation n squared over root n to the 6 minus 4. Where did we see that before? That's this series over here. That's the series we got when we plugged in x equal minus 5/2. We already know what's happening with that series. We already know this series is going to diverge, right? So this series was previously shown to be divergent, okay? So the power series does not converge absolutely at this point, but it could still converge, right? It could still converge. It just means it doesn't converge absolutely, but it could still converge. So what we need to do is actually work out the full series, the original series. Instead of taking the absolute value, that didn't help us, right? We took the absolute value, that didn't help us. So we actually need to tackle this series head on. Okay, but notice here's where the alternating series test comes in. Notice that these terms are positive and decreasing, right? As n gets bigger and bigger, these terms are getting smaller and smaller, and it is decreasing towards 0. And the minus 1 to the n in front causes the sign to alternate. So this is an alternating series. So by the alternating series test, it converges. Okay. So we will say that the power series is conditionally convergent at the point x equal minus 3/2. Conditionally convergent means the series converges, but if I look at the series of the absolute value, it will diverge. Okay, so how to write all of that? Last final statement is, therefore, the interval of convergence of the power series is, so it's your original interval, but I need to add in this endpoint. So close the bracket here, add it in. With absolute convergence for x everywhere inside the interval, right? And conditional convergence at the point x equal minus 3/2. Okay, so it's saying that this point over here, it did not converge. This point over here, it converged, right? But not absolutely, right? So that is the story. That is the end of the series, of the power series section. So there are quite a few practice questions and examples in the practice sheet. Okay, also in past papers, you will see that power series tend to always come in the last question. So you have a lot of examples, a lot of questions. So sit and try them, right? If you get stuck, you could always send me an email about it. I could try to help you. Okay, but sit and try to do these power series questions, right? If you could work out the interval of convergence for a power series, then that actually captures everything in this chapter, because you need to apply all these different rules to it. Okay, so try to work out all of that for a power series. Okay, so that is the end of this chapter, right? So that's it for all our material. Are there any questions?